Hello everyone, and welcome back to the series of lecture on actinide chemistry. In the last lecture we have discussed about the term symbols, and we have also tried to see that how we measure this UV visible spectra of any ion, give it a lanthanide or actinide. And we have seen that the three types of transitions are possible in lanthanides and actinide, that is intra-configuration transitions, that we also known as FF transition, interconfiguration transition, that is known as FD transitions, and the charge transfer transitions. When you are having electrons in the f orbital, then the two transitions, that is interconfiguration transition and intraconfiguration transitions, are possible. But in cases when you are having no electrons in the f orbital, then whatever transition we see or whatever color we see in the compound, that mainly comes from the charge transfer transitions. And one of the very good example of actinide that gives this charge transfer transition is uranyl ion, because if you see uranyl ion, it has a F0 system. So if you compare the electronic spectra of lanthanide and actinide, the lanthanides have bit more sharper spectra but with a lower epsilon, whereas actinides, they are having a bit broader spectra, and because of more diffuse nature of the 5f orbital compared to the 4f orbitals, they have more intensity and they are more participative in the reactions compared to the lanthanides. So let us see some of the spectra, but this is the term symbol that we have already calculated, and if you remember, then we have calculated the term symbol for europium 3+, which is in F6 system, and we have seen that if you just calculate the term symbol for this, you are getting 7F is the term. And if you just use the coupling, LS coupling, you are getting a value from 0 to 6. And out of this 0 to 6, we have used the Hund's rule to get the established configuration or the ground state configuration. And there we have seen the ground state is nothing but 7F0, because it is less than half filled. And if you see this spectra, the ground state is 7F0. So here in this particular figure, the ground state of all the trivalent lanthanides are given, from where the transition will start up to almost 40,000 centimeter inverse. And you can see for europium it is 1, 2, 3, 4, 5, 6, and again you start from the 7F, now you reach to the 5D, and then again 5H, and so on. Similarly, if you just try to get it for neodymium, that is Md3+, which is an F3 system, you will get a state that is 4I9/2. I hope you can derive this state, and you can at least say that out of different states that you derive using this term symbol, that which one is the ground state, because that is the state from where the transition will start, because we are talking about the FF transitions, and from there the transition will start, and depending on the different selections rule that can apply for a given transitions, we can get different transitions like this or this or this. We'll just see some of the spectra, that how they exactly look like when you record the spectra in the aqueous medium. So this is the percolated salt spectra and dissolved to the water medium. So you can say that starting from praseodymium, then neodymium, and then samarium. So you can say the both are having some F electron, so they are mainly having either FF transition or FD transition. As we have seen that the FD transition is mainly prominent in cerium, praseodymium, and terbium. These are mainly dominated by the FF transition. If you just look carefully the spectra, the first thing you can always see is the epsilon value. It's very low. It's less than maybe 10 in many cases. Whether you choose any of the lanthanide ion usage in the trivalent state, this is very low. This is because these are mainly FF transitions with the del L is equal to 0, so they are parity forbidden, they are not allowed. But because of some admixture of the different parity into the F orbitals, we see this transition, but again they are not allowed, so they are having very weak intensities. Now one thing, if you see very carefully, that these are very sharp transitions, and again the sharpness comes from the deep buried orbitals, because we are the transition is between the F and F orbitals, so they are deep buried and not having much influence from the external environment. The other selection rule that we know del S is equal to 0. That the spin change, or you can say the spin multiplicity change, should be 0. And here you can again see that your initial transition or your ground state is having spin multiplicity of 2s plus 1 is equal to 3. And if you see that a transition in which suppose this is not followed, and again as I said that this is not allowed. So if you are having this and this, both possibilities, that it is a laboratory forbidden and your spin is plus minus 1 but not 0, then it is called doubly forbidden transition and their intensity is again decreased to a large extent. I'll just repeat it again for clarity. What I mean to say that the spin multiplicity should be same when you are having a transition. If your spin multiplicity is changing in a transition, their intensity falls drastically because this is forbidden transition. So ideally your del S should be 0 for a transition to be allowed. And here again you can see your spin multiplicity is 3 and here it is 1. So here you can say there is a change. So this is not allowed transition. And because of that the intensity is very weak. But if you compare this with this, these transitions are comparatively more allowed and having a better intensity. Obviously, if you compare the same multiplicity, then again the overlap between the orbitals and other admixtures come into the picture. But generally, if you are having a transition with the same multiplicity, they are fairly more allowed compared to the transition which is changing both. There is no change in the FF or del L value, and there is a change in del S. So these kind of transitions are not allowed. Here again you can see, if you just see this spin multiplicity, then it is 4, and whatever is with the 4 they are bit more allowed compared to the one with the lower numbers. Here I have marked a peak with the red color. Some of the transitions are very much affected by the environment, although we say that these are the inner orbitals, but still they can have some influence on this kind of transitions, and they are known as hypersensitive transitions. This is one of the hypersensitive transitions that is occurring in the Newtonian spectra, and people use this kind of transition to get information about the conditioning structure, the metal-ligand complex, the nature of metal-ligand complex around in any phase. You can say in solutions also. I will again show you the spectra of samarium, and in a very similar way you can see the spectra of other ions like as europium. And here you just remember this peak. It's a very important peak when we talked about the luminescence spectroscopy. But just for that reason I just want to remember this, that you have a transition from 7F0 to 5L6, and that happens around 394. If you see, this is around 394. So this is one of the most prominent peak in the europium 3 spectrum. Again you have different prominent peaks. So what is the use? One of those use of these transitions are, and you can say the colors that you are getting. You can see in all these we are having some transition in the visible region. When I say visible region, I am talking about maybe 400 to 700 region, maybe in this region. And you can see there is certain peaks. So always in this region there are some peaks, and as I've told you in the previous slides that when you are having some band, it will give you something called spectral color, and when you have some spectral color, the complementary color is visible to you. And since all these are having some peaks in the visible region, here again you can see the list. This again, you see this is almost white. If you see this, I just remove this for clarity, and if you just draw the 700 and the 400, you can see there is almost no peak, or maybe very small. In certain cases you can say the intensity is so low. So if you see, most of the time if you have an europium salt, it is almost time colorless. It is colorless. Similarly, if you have a terbium salt, not very good color. But if you take the oxide, that is 92/3, this is a very good blue color. whereas most of them are colorless. These do have some color because again you can see some transition to the visible region of the spectrum. So whenever you see the transition in this region, you can expect some color when you prepare solutions of this kind of lanthanide. But if you are not able to see any peak in this region, they should be colorless. Here I have just tried to compare the spectra of trivalent lanthanides with trivalent actinide. Here we have taken example of europium, and here it is americium, and we know that it is both are same F6 system. One thing you can directly see from the spectra is the epsilon value. See the epsilon value, it is less than 4. But here if you see the epsilon value, sorry, this is the optical density. So we have to calculate the epsilon value using the relation E equal to PCl. So absorbance you know from here. E you have to calculate, and concentration is given. So you can calculate this for the path length of 1 centimeter. So you can calculate, and we found that the epsilon is very high. So you can see that they are trivalent in nature, europium 3+ and americium 3+. And since they are having involvement of 4F and they are having involvement of 5F, and as we have said initially that the 5F is more diffused, and because of that the interaction, or you can say that perturbation in 5F is more compared to the 4F. So these transitions are more allowed, or their epsilon is on the higher side compared to the transition in the lanthanide. So this is one of the example I've given for the transition of trivalent lanthanide and actinide, where you can directly see that. It's very difficult to tell about the broadness, but in general the 5F should be more broad compared to the 4F. But here since the scales are very different, you may not be able to get it straightforward, but their broadness should be on a higher side compared to the broadness that we observe into the lanthanides. So we have taken care of the trivalent. Let us see that how the tetravalent and pentavalent actinides look like, because in lanthanide we are mainly talking about the trivalents because their group oxygen state is +3. But when you talk about the actinides, you can have +2 to +7. So let us see that how the other oxygen states will look like when you talk about the actinides. You see the actinides, as I showed you that their oxygen state can be varied from +2 to +7. You see almost all the oxygen state have some color. Everybody is giving some beautiful colors, and some of the real solutions that reported in the literature, if you see those colors, it is, suppose you take the neptunium solution. This is neptunium in different oxygen state. It is like from 3 to 7. So it's like 3, this is 3, this is 4, 5, 6 and 7. If you see, there is a drastic change in the color when you are moving from 3 to 7. Suppose you take the plutonium solution again. There is a beautiful color that changes from the 3 to 7. And the more interesting thing, you can see this diagram. Everybody is plutonium 4. What we are changing is the media. We are starting with an HCl media, then perchloric acid, then nitric acid, and finally we are making some colloids, which is again in aqueous media of little higher pH. So you can say, although everybody is plutonium 4, still their color is different. Why? Because when we are having different kind of complexing anion into the media, even they can very well interact in a very different way with the 5F orbitals of these plutonium ions, and because of the splitting of those orbital in the presence of different kind of complexing anion, they gave very distinct UV spectra, and some of the lines are getting maybe allowed and some of the lines are getting forbidden, and that causes change in the color because now you are having a different spectra, different perturbations, different F orbital splitting in the presence of different kind of anion. So you can see that just by changing the anions you can change the colors here, and that says that how strongly this F orbital, the 5F orbital, has influence, or how strongly it can interact with the external environment compared to the lanthanides. If you see the spectra, neptunium 3 will look like this one. Neptunium 4 is again looks very different than neptunium 3, neptunium 5, then neptunium 6. One thing I just want to mention here, if you see the spectra, everybody looks a bit different from other. Suppose you see Neptunium 4, it has 2 peaks. But if you see Neptunium 5, it is having only 1 peak. And if you see Neptunium 6, it is having a peak but in the NIR region. The peak position is around 1225 in this case. It is around Neptunium 4, so it is around 964. It is around some 715 or so. It is around 980. So you can see that every oxidation state has some different peak, or you can say they have some distinct spectra. So we'll try to use this information when we study the applications of this UV spectroscopy into the electronic chemistry. Do remember this, that they have very different spectra. Again, we have seen the spectra of Neptunium with different colors and with different wavelengths. And here again, just if you correlate again with the color, you can see this region, maybe up to 700 or 750 region. You are getting some peaks here. Here also you are getting some peaks. So here you see, although this intensity is very low, but still it is enough to give you very good color. So whenever you have some peaks in this region, then definitely you are bound to get some color into the solution. And this intensity of the color will depend, obviously, depending on the epsilon, or depending on the strength of these peaks, that how strong these peaks are absorbing, or how strongly they absorb the light. So depending on that, you will get the corresponding complementary colors. We'll see the UV spectra of the plutonium. Again, I've shown you that from 3 to 6, when you go, you are getting different colors. If you see the spectra, then 3, 4, and 6. I have not shown you the spectrum of plutonium 5. And I hope by the time you are able to understand that all these 5, whether you are talking about plutonium 5 or uranium 5, they are very unstable with respect to the disproportionation, and because of that, the getting spectra of plutonium 5 is not that straightforward. It will get disproportionate and in the acidic solutions, and if you are using too much of basic, chances of hydrolysis is there. So because of the disproportionation, we are not giving the spectra of plutonium 5. And all these spectra, where plutonium 3, 4 and 6, they are not that easy to form. As I told you in the very beginning that one of the most stable oxidation state of plutonium that exists in water is generally +4 in the acidic media. But since their redox potentials are very close to each other, so in solution you will get ideally all these 3, 4, 5, 6, everything should be there in the solution, and 5 will be there, but will be disproportionate to 4 and 6. So we are mainly getting 3, 4 and 6, and then you have to stabilize them to get a spectra, because you cannot have a mixture of all these things and you cannot record the spectra. So you have to stabilize them before recording the spectra, and these are some of the reagents that are commonly used for the stabilization. For plutonium 3, we generally use hydroxylamine hydrochloride. For plutonium 4, it is the sodium nitrate. And for preparing plutonium 6 solution, we generally use an oxidant, that is HClO4 itself is acting as an oxidant. We use this powder, plutonium oxide or plutonium oxide solution in a solution form. We add perchloric acid, we do 2-3 times dry, and then we again dry it, and we again add HClO4, we again dry it. By the time we are not getting a spectra that is characteristic of the plutonium 6. Here I have given you the different peaks and their molar absorbability for the plutonium solution. Here I just want to emphasize that if you see, you are changing the medium and there is some change in the peak position and molar absorbability, that is because you are changing the ligand, and that we have seen also when you are moving from HCl to HNO3, you can see there is some changes in both in molar absorbability as well as in wavelength. And we'll try to see that since I've shown you that when you are having a HCl and this is HCl and this is HNO3, you can see almost one is, you can say, orange and one is green. So you can see that just by changing from chloride to nitrate, the color has been changed. And first thing I want you to notice that if you are starting from plutonium 3 and going to plutonium 4, there is some spectral changes that I have already shown here. When you are starting with plutonium 3, and plutonium 4 is having some spectral changes, and when plutonium 4 and plutonium 6 there is again some spectral changes. So if you are having plutonium 3, you can easily identify this, yes, this is plutonium 3. So if you add nitric acid to plutonium 3 or HCl to plutonium 3, there is change in these peaks. With increasing acidity there are some changes, and these changes directly correlate some interaction between plutonium 3 and nitric acid and plutonium 3 and chloride ion. So to understand the kind of interaction and the nature of species that has been formed in different conditions or different acidity strength, we can use this kind of spectra. Here again the same thing is for the plutonium 4. Like similarly we can see for the plutonium 6 also, there is a constant decrease when you are adding HCl, because it will lead to formation of different species of plutonium in the hexavalent state. So because of the change in the speciation, there is a change in the spectral intensity. Nitric acid again, there are certain changes, and from these changes you are able to tell that yes, the species are different. The species that exist at 1 molar may be very different from the species that is existing at higher molarity, maybe 9 molar HCl in this case and 10 molar nitric acid in this case. So in this table you can find that most of the actinides that we generally use in for our different kind of studies, that they are like plutonium, americium or neptunium, and different conditions in which we generally prefer to store them. Or so the spectra that is in different conditions are given in the previous slide, that is in nitric acid as well as HCl medium. But here we have just compiled the data in the perchloric acid medium. Why? Because the perchlorate, that is HClO4, is having an ion that is perchlorate ion, that is ClO4 minus, and this is kind of a non-complexing anion. And when we record spectra in this kind of anions, what we assume that whatever spectra we are getting, it is the spectra of the particular lanthanide or particular actinide having a very less perturbation into their coordination sphere because of the presence of perchlorate ion. So the levels are not very much get splitted. So we say that it is something called not exactly free ion, but very close to the free ion spectra. And you can see that different ions have different lambda max and different molar absorptivity constant. For example, if you say that neptunium 5, it is having major peak around 980, whereas if you see neptunium 6, it is having a peak at major peak around 1225. Again neptunium 4 is having peak at around 960. So just by recording the spectra, you can see we are having information about the different lambda max. From the table you can get information about the different lambda max and their Emax, and that is useful when you are trying to identify a proper species, or you can say a given species, into a medium. So these are the applications of the absorption spectra. In general, we can use them basically for the qualitative analysis. That you have a system, suppose you want to understand that okay, I have given you some system and you want to understand that what is the particular oxygen state. Suppose I give you some solution of plutonium or neptunium or any other actinide or lanthanide. The first thing you want to understand that okay, what is the oxidation state of the metal ion is there in the solution. You can just record the spectrum, and as I've shown you, and you can see from the list and you can see from the previous spectras that different oxidation states have different lines. And just by looking the spectra, you have an idea that yes, in my solution this is the most prominent oxidation state. You can have a mixture also. Even in the case of mixture, suppose I am having a mixture of neptunium 5 and neptunium 4. So if you are having a mixture of both, suppose neptunium 5 and neptunium 4, then we know that neptunium 5 peak is coming around 980 and neptunium 4 peak is coming around 960. So even if you are having mixture of oxidation state, just by looking at the spectra, you will be able to tell yes, this is the oxidation state that is present in my system. So one of the very crucial information that you get is the qualitative analysis. Just by looking at the spectra, you can get information, yes, this is the ion, this is the oxidation state that is present. Second thing is that can we make some quantitative analysis out of this? Answer is yes. Why? Because here in this table, as you can see that we have given you the epsilon values for different metal ions, you can see. And we all know that from the Lambert-Beer law, E is equal to ACM. Suppose you measure certain spectra. Again, I am just taking example of neptunium. Suppose you measure neptunium spectra, neptunium 5. You are getting a peak like this, which is around 980. You get some absorbance. And what you want to calculate, what is the concentration of the neptunium ion in the solution. And suppose you are getting a pure peak of neptunium 5. And you can just use this epsilon around 395, 1 centimeter, absorbance, whatever you get from here, and you can calculate the C. So this can be used for the quantitative estimation as well. In cases, even if you are having a mixture, then depending on the peak positions. But suppose you have a mixture of neptunium 4 and 5. So neptunium 4 is coming somewhere here and neptunium 5 is coming somewhere here. The 4 is around 960, this is around 980. Even for the mixtures, if the peaks are well resolved, you can easily get the quantitative information that, okay, how much of the neptunium is present in neptunium 5, how much of the neptunium is present in neptunium 4. So it can also give you information about the quantity. So you can do some quantitative analysis also. Similar is the case with plutonium also. You can do the quantitative analysis of any other actinide that you want, provided you know the epsilon in that particular media, because epsilon do change depending on the media. So to get the knowledge of the quantitative analysis, one thing should be always taken care, the media in which you want basically to get the quantity. You should have the epsilon for that particular media. We can study the redox reactions. What I mean by the redox reaction, we all know that they are very redox sensitive. Both actinides are little more redox sensitive because lanthanide do have +3 oxidation state in most of the time, but the actinides are rather very redox sensitive. And suppose I want to study some reactions. Let us assume that I want to study some disproportionation reaction of let us say example of neptunium only. So you will have a spectra like neptunium, and I want to study. I have chosen this because it contains all the oxidation state of neptunium. So if you see this reaction, you are having neptunium 5, you are having neptunium 4, you are having neptunium 6, and all these three, neptunium 5, 980, neptunium 4, around 960, neptunium 6, around 1225. All these things are way apart from each other. And suppose I want to study the redox conditions in which this reaction is complete, or I want to understand that at what acidity, what is the kinetics of the reaction and how the reaction is going on. What we can do, we can start with this at a very zero time. In this you will get only 980p, but as the time will go on, suppose you have fixed the acidity, you will start seeing these peaks. So we can follow the redox reaction, we can follow their kinetics, we can also follow many times the mechanism in different kind of redox reaction using these peak informations. And since we have shown that they even vary, the positions and the epsilons, they do vary, not very much, but they do vary depending on the ligands you add. So here I have just given you an example of some titrations that how the ligands will affect the complexation. So here, just for example, suppose you have a solution in which neptunium is coming around 976 nanometer. This is the solution which I have specifically prepared in some kind of ionic solvents. So the peak is not at 980 but a little on the lower side. But suppose you have some transitions that is coming at certain peaks, and in that particular solvents I have added some ligand, and you can see that peak is shifting from the 976 to 991. So by the shift you can get, yes, some of the neptunium has been complexed, and if you keep on adding the titrant or you keep on adding the ligand, you get a spectra like this, and we can use different mathematical equations to get the exact complexation constant between this neptunium 5 and that particular ligand. And we can also get information about the epsilon of both neptunium 5 and neptunium 5 and whatever L you are going to use. So those information we can directly get from the absorption spectra. And detection and estimation of lanthanide and actinide ion in the environmental sample. This is one of the very important thing that we can do with this, as many time you can see the Emax is very high, more than 100 many times you see. So what does it mean? It means that when you use an equation and you have a spectrophotometer which is quite good enough that you can easily measure 10 to the power minus 2 order of absorbance in the range of 0.01, I should say, absorbance. If you are having a spectrophotometer of this kind that can easily measure 0.01, then if you put this value as 0.01 and suppose your epsilon for such a species, let us say this is more than 1000, so you can say it is 1000 C into 1. So what you can say easily, that C is nothing but 10 to the power minus 5 molar. So here you can say, even just by simple measurement, you can get an idea about the concentration, and that too a very low concentration. Because when we talk about the environmental sample, the concentrations are very low. In fact, much lower than whatever I've shown, 10 to the power minus 5. And many cases we use some chromophoric ligands such as arsenaljo to get an very high epsilon for that particular complex. And for that we just mix the actinide or lanthanide that we want to get the information of the concentration with that particular chromophore. Then we record, and there the beauty is that the epsilon goes to as high as 10 to the power 5. And if your epsilon is such a high, you can easily go to very low concentration of the lanthanide and actinide, and you can really see the samples into the environmental media. With this, I would just like to end up today's lecture, and we'll meet in the next lecture. Thank you very much.